Hello and welcome to another ramble, hopefully, with me. Today we're looking at IEB's May 2024 Paper 1, Question 12B. I'd like to give a quick shout out to someone whose handle I'm going to butcher, and I'm very sorry in advance if I do. Parul K J2N, who specifically asked for videos covering this question and the question that came before it. So the funny, not so funny thing is that I had already recorded a video for 12A, and I was just so dissatisfied that I couldn't figure out why that solution works. Really, I just guessed, and that guess happened to be correct. And I don't like, giving solutions like that because it's half-baked anyway. But when I got this comment from this user, that kind of jolted me out of my agony and this rabbit hole I was in of trying to perfect the 12A video. So I'm going to release the video for 12A as unfinished as it feels, and you will now also have the video for 12B, and then we'll be done for the series, unless of course any of you wants to get a video on a question from this paper that I didn't cover. You are more than welcome to also request. Okay, right. The rambling has already begun. Let's ramble about the question. So, you need to fence your vegetable garden A, B, C, D, E, F as shown below. Okay. FE is, okay, wait, I need my little pointy thing. FE is parallel to DC, which is also parallel to AB. And then AF is perpendicular to FE, okay. AB is Y. AF is equal to DC, which is 2x, and BC is equal to x. It's already coming back and we aren't even very far with this question. Oh, there's also the statement of parallelness that I missed. AF is parallel to DE is parallel to BC. Okay, so before we even get into the details of this question, I'm just going to write the information that we were given here just symbolically. Okay, so those are all the sets of parallel lines we're given, and we're told that AF is perpendicular to FE. So pretty much what this establishes for us is that all these lines are at right angles to each other. If you do like corresponding angles and all of that fun stuff, this is also a 90. This will also end up being a 90. This will also end up being a 90. So just by giving us this information is just to tell you that none of these lines are weird, slightly skew lines or anything. You can just treat this like a rectangle with a rectangle that's been chopped out of it, Anyway, so the meat of the question says, if you have 20 meters of fencing, then determine the value for x so that the maximum area is enclosed by the fence in the shape used above. Okay, so we only have 20 meters to do this perimeter. But we want to make this space as big as possible. So, what is the x that will maximize our area? So the first thing that jumps out to me is we're trying to optimize x, but there's also this weird y in the mix. I don't really like that. I feel like this whole conversation should just happen in terms of x. That will simplify matters so that we don't have to think about a second variable. However, that being said, I don't know if there is a way to get rid of this y. We know that this is 2x. We know that this is x. We know that this is also 2x. Okay, so I'm just going to fill in this little piece over here to help me think about what's happening. So because this whole side is 2x, and over here we're told that this bit is x, so that means that this little piece here is x. So in other words, DE is also x. Okay, and then we have this side being y, so this side is also y. This piece is 2x, so this piece over here will be y minus 2x. So the perimeter of our vegetable garden will be given by 2x plus x plus y minus 2x plus 2x plus y plus another x. And that has to add up to 20. Okay. Heaven. So this y is really just going to be among us. Yo. It's giving me heebie-jeebies. Very severe heebie-jeebies. Okay, I'm just going to go along with it because for now I don't see a way to avoid it. Yeah, let's just go with it for now. So the perimeter of the shape is in fact a function of two variables, x and y. So that is going to be y minus 2x, which is that side, plus 2x plus y plus x plus 2x, and lastly plus another x. Okay, so what does that all add up to? So I've got oh, how's that picture? Okay, y plus y. Hey, let me use my fancy highlighters here. Y plus y, and that's 2y. Okay, now I'm just left with x's. So I've got minus 2x plus 2x, so those are going to cancel out really. And then plus x plus 2x plus x, so that is 4x. Okay, so that's the perimeter. And we are told that 2y plus 4x has to be equal to 20. Yeah. Supposing that, I mean, I think it's fair to assume that the maximum area will occur with the maximum amount of fencing we can use. There isn't going to be a situation where somehow by using 10 meters, only 10 meters out of the 20, you end up with more area. I don't think that's feasible. Anyway, so 2y plus 4x must be equal to 20. So that's the first. Okay, it's giving maybe simultaneous equations are coming somewhere, somehow. Let's see. So the thing we are trying to maximize is the area. Ne? This area here. So we need to come up with an expression for the area. How you do that is completely up to you. There's a couple of options. The first option is you can take the area of this big rectangle and then minus the area of this one. Honestly, I think that's the most straightforward. Otherwise, you can chop the shape up. So then you take the area of this plus the area of this rectangle. You can chop it over here and find an expression for this area, and you know, all of those things should work. I'm going to go with the difference. So again, the area is going to be a function of two variables, x and y, and it will be given by the area of this whole rectangle, which is 2x times y minus the area of this little rectangle here, which is 2x times x, right? So that is going to be 2x squared. Hey, it's very weird to write this on different lines, honestly. So let me fix that. Hey. Yeah, you can tell when I haven't recorded in a while, like it's so crusty with this app. Yo, now my minus is just in no man's land. Okay, right. So that is the area of the vegetable garden, and that is what we're going to try to maximize. So now my problem is, you know what? The thing. Okay, because, let me tell you what I'm thinking. So the first thing I'm thinking is, how on earth am I going to find the first derivative of this expression when there are two variables? We don't know how to do that in high school. We find out how to do that in university. So I'm thinking we're not going to find the first derivative here because what in there? So I'm going to think of the problem from another perspective. I'm going to say the maximum area will occur when this rectangle here is as small as it can possibly be. Yeah, I think that's a fair thing to say, right? Because the area of the vegetable garden is the area of this big rectangle minus this, right? So if we can just minimize the area of this guy, isn't it fair to think that that is the smallest? No, that's a zero, Shem. That's a zero because I can already see that, okay, the area of this little rectangle is given by that expression, and this is going to be the smallest when x is 0, and that's not really an option because when x is 0, then we don't have this side. So Shem, sorry, it is a 0. The next thing that I am tempted to think is, what if I just treat the y like a constant? So instead of trying to optimize both the x and the y somehow, I just treat this y like I fix it, treat it like a constant, and just try to optimize for x. Yeah, I think that's what I'm going to do. I don't feel good about it, honestly, because why choose to optimize the x and not the y? Or maybe it works if you optimize on either variable. I don't know. I'm going to try optimize on both just to see. Anyway, but first we're going to optimize for the x and see where that takes us. So first derivative. So I'm going to actually then remove the y here as a function, a variable, and pretty much just treat it like a constant. So it's not a variable, it is some constant number whose value we don't know, but it's a constant. So the only thing we care about changing is x. So the first derivative will be over here just 2y, okay, because we know that if we have 5x, if we have some expression is equal to 5x, the first derivative will just be 5, right? The x will disappear. So that's the same thing that's happening here. Okay, so that's the first term, and then the second term, that's pretty straightforward. That looks like that. So we are looking for the place where 2y minus 4x will be equal to 0. That is where the area will be a maximum. And that kind of makes sense because this is a parabola if we're looking at what's happening with the x. And it's an upside down parabola. So it is a parabola where we reach a maximum value. And we are trying to find the x where that maximum value occurs. Okay, so then we have equation number 1. We know that our fencing, the perimeter must add up to 20. And then we have equation number 2, which is the x value that optimizes the area of the vegetable garden if we fix y, if we say y is a fixed value. Right, so let's just solve this system of simultaneous equations. Okay, that 2 is looking very sketchy. Okay, so there's our first equation and our second equation, and you know, I love me some elimination, so I can just add these two equations together. So I'll have 4y, then 4x minus 4x cancels out, and then here we have 20, and then we will say, okay, y must be equal to 5, which we can then sub into either of the equations. So 2 times 5 minus, I'm using this equation, minus 4x is equal to 0. So that is 10 minus 4x is equal to 0. And then, you know, you can do your magics to find that x is 2.5. And that would be, those would be the values for which our vegetable garden allegedly will have maximum area. So let's go back to my question of here we had an expression for the area of the vegetable garden, which is in terms of both x and y. So now my question is, if I were to optimize for the y, so treat the x like a constant and instead optimize on the y, would I still get the same answer? So what would have happened? Let's time travel a bit. So my area expression, we said technically is in terms of x and y, and it is 2xy minus 2x squared. So if I now decided that, you know what, this x is in fact not a variable, it's some constant whose value I don't know, but it is some constant, and really the area only varies because of the y. So now the x would be a constant and the y would be the variable. So if we then differentiated this expression, now this term would just be 2x because this is the coefficient of y, and this term over here would be a constant, so it would just fall away. So the first derivative would be this guy over here. And if we look at this function, this is pretty much a straight line, right? This is blah blah is equal to my plus c, some constant. And that doesn't really have a maximum value. What is happening? A straight line doesn't have a maximum value. So what would this even mean? Yeah, so if you were to try and solve which value of y maximizes this, there would be no solution really, because this number is what it is no matter what y is. So that would just be a dead end. Hi. So once again, here I am feeling like I just made a lucky guess, and the lucky guess maybe works. I don't like it. I don't like it. I want to know why the y is not important. I guess maybe because the question says we are optimizing on x, so we don't really care about y varying. And us guys, I don't know. I'll have to sleep on this one, but okay, for now this is the best I can do. Let's see what the memo says. Maybe the memo will have revelations. So the memo simply says fe is equal to y minus 2x. Yes, we said that too. And then it comes up with an expression for the perimeter, which is this. And then it says, based on this, oh, it gives us an expression for y. Oh, I see. Oh, yo, now my answer is wrong, wrong, wrong. What a shame, what a shame. What a shame. Okay, so let's get rid of all this bogus. So this is where I'm going to be playing some elevator music as you wait for me to erase all of the nonsense I've written here. Yo, I would have gotten 1 mark here. How much is this out of? It would have just been 1 mark for effort, not for speaking sense. Yo, this number 12. Shame. They really brought out their bazookas. Looking at the memo now, I'm like, yeah, that was obvious. But clearly it wasn't. Clearly it was not. So what they have done is they have said, look, the relationship between x and y is given by the perimeter. We know that this has to add up to 20. So we can use this to express the one variable in terms of the other, so that we are not dealing with a situation like this where we have an expression of the area that has to do with x and has to do with y. We don't want that. We need an expression that is just in terms of the one variable. So if we can just rewind. So we're taking this equation, and yeah, you can work either in terms of y or in terms of x. So it's up to you. Okay, I mean, I guess they specifically ask you to optimize on x. So if they had asked you to optimize on y, you would have taken this equation and gotten an expression for x, so made x the subject of the formula, so that you can get an expression for x that is in terms of y, and then you can replace all your x's with this expression that talks about y's. Anyway, so we are trying to get rid of y, so we are going to get y by itself. Okay, and then divide by 2 throughout. So then that is my expression for y in terms of x. Cool. So then we say the area of the rectangle in terms of x and y. So that's pretty much what we did before. That's going to be 2xy minus 2x squared. And then now we can write it as a function of just x. We can replace the y here with 10 minus 2x, right, which is coming from, so this is coming from this over here. Nice. Yo, Aisha, I'm definitely kicking myself for this one. 20x minus 4x squared minus 2x squared. This is actually one of the nicest questions to end with, honestly. This was a very nice optimization question. Okay, so now to see when our area is at a maximum, and again we can see that the area function is a sad parabola, so it does indeed reach a maximum value. So we want to see which x value maximizes it. So we take our first derivative, and then we say, okay, when is it we solve this equation, right? When is it equal to 0? So we are solving 20 minus 12x is equal to 0. 20 is equal to 12x, and then we divide by 12, right? So that simplifies to 5/3, and that is in fact the correct answer. So I would say the moral of this lesson is, if you know you're doing something dodgy, maybe just reevaluate whether you should be going down that path. Really, because you had me with my suspicions initially, but then I carried on with my nonsense. So yeah, it's just unfortunate that I can't say the same for my previous video 12A, where I was just going on a guess and the guess happened to be right. So on this very somber note, we conclude our series, and we hope for better days with paper 2. Catch you then.